With an understanding of waves, we can now talk more specifically about sound waves. And sound waves are an example of a longitudinal wave that we talked about at the start of this unit. And longitudinal waves come from vibrations that cause compressions and rarefactions in the air. And I say in the air because that's the most common way that sound waves are able to travel, is through the air, but it actually could travel through any other medium, any other collection of particles. So it could travel through water or any other liquid. It could also travel through solid materials as well. But specifically when it does travel through a specific medium, that is what is creating those sound waves. So again, it is a longitudinal wave, but it could be in the air or in water or any other material that has particles in it, and that will transfer the energy down the line and allow the waves to still move. So there are, of course, many examples of things that create sounds. Really, anything that vibrates at all will create a sound and cause some compressions and rarefactions. But common things are your vocal cords, which vibrate and push a little bit on the air and set up that pattern. A guitar string that vibrates, it will vibrate back and forth in a particular pattern as well. But even just an engine that's running, something that's vibrating or rattling, is going to push on the air particles a little bit around it in a specific pattern, and that's going to set up a sound wave. To try and see how these sound waves are actually created, though, one really simple thing that creates sound waves is a tuning fork. And tuning forks are used for tuning purposes because they can create a very distinctive sound, a very specific pitch of sound, because they create very simple vibrational patterns. So, for example, in the first stage, picture A, we've got two different prongs, A and B. And right in that stage, nothing is actually happening. So that would be just the tuning fork sitting in your hand before you actually hit it. And so all the air particles are just represented by those vertical lines in a row beside it. And they're evenly spaced, just the same way that the average spacing between air particles when they're normally sitting in a room will be fairly equally spread out. But in stage 2, now what's happened is the tuning fork has been struck, and those two prongs start to vibrate back and forth. And specifically in stage B, we're showing that prong A has been pushed and now vibrates or rocks towards the air particles to the right of it. And what that's going to do is push on those air particles and cause them to bunch up. And when they bunch up, that causes what we call a compression in this area here. So that causes a compression. Then, remember that that prong will naturally swing back the other way. So stage C is showing what happens when we have the tuning prongs that swing back the other way. So now, prong A has swung back towards prong B, and rather than causing the air particles to bunch up to the right of it, it's actually allowing the particles to spread out a little bit in this area beside it. And when the particles are more spread out than they normally would be, it's the opposite of a compression. It's a rarefaction. But remember that compression from before is still on its way traveling down the line. So at that stage, as it starts to rock back and then forth again, we get a compression that's already traveling and now a rarefaction being set up. By the final stage, in picture D, we're representing the fact that the prongs will continue to vibrate back and forth and back and forth. And so that will continue to set up an alternating pattern of rarefaction and then compression and rarefaction and compression and so on. And every time we go through one full path of a rarefaction and a compression and then on to the next rarefaction, that is one whole wavelength or one lambda of the sound wave. But of course, this is much easier to visualize when you can actually see it in motion, because these particles aren't stationary, they are constantly moving. And so this is what would be happening with a large collection of air particles. The moving red line at the left hand is sort of representing like the prong A from the tuning fork. So that's vibrating in and out, pushing on the air particles, and then traveling back towards the left again. So in towards the right, pushing on the air particles, and back towards the left. The little red dot that you see is the location of one particular air particle. If we just were to look at the location of one particular air particle and see what it's doing, it actually doesn't travel all the way down the line like the wave's energy does. Each particle is actually just rocking back and forth. It's moving away from its normal rest position and then swinging all the way back and sort of vibrating just back and forth horizontally. But overall, you can see that the wave energy is moving the entire way down the line. Those compressions are clearly noticeable, and then in between them you see these areas where the particles are much more spread out. Those are the rarefactions. So the key that we have to keep in mind in all of this is that any of these mechanisms that produce sound, they all require a medium for that sound to be produced, which means they need some kind of particles in the way. It's just a collection of particles. So they could be air particles or water particles or some thick liquid like molasses or even a solid like iron or steel. As long as there's particles that can vibrate and transfer that vibrational energy down the line, we can produce a sound wave and allow that sound wave to travel. But you may have heard that, for example, in space, no one can hear you scream. And that's just a way of saying that generally sound waves don't travel through space the way that they do here on Earth. Because typically in space, you don't have a huge collection of particles like air particles that we have in our atmosphere to transfer that energy. Most of space is what we call a vacuum. There's no particles at all. And so there's nothing to transfer the energy of one vibration down the line to somebody else's ear. So typically we say that sound waves, unless there are lots of particles in the way, cannot really travel through space. In general, they can't travel at all through any kind of vacuum. Because in general, if the medium was not present, the tuning fork would still vibrate, or whatever the object is would still vibrate, but there would be no effects. They would have no other particles to push on. And so there wouldn't be any way to set up that pattern of compressions and rarefactions. Now, we'll talk about more of this as the unit goes on, but sound waves, of course, can also travel at different frequencies. So the number of compressions and rarefactions that we see per second affects the frequency of the sound, of course, and to our ears, we call that the pitch of the sound. So higher frequency sounds, when we see more compressions and rarefactions per second, that leads to a higher pitch sound, or what we sometimes call treble. If there's a lower frequency, so not as many compressions and rarefactions each second, we hear that as a lower pitched sound, and we call that bass. As I said, though, we'll talk more about different pitches and how that relates to music as well a little bit later on in this unit.